Imagine you have a surface like this one. This is the top half of a sphere. I want to define a concept called orientation of a surface. And it's going to turn out that some surfaces are going to have this property of being orientable and some surfaces are not. So what's the idea? Along this half sphere, I could put up a field of normal vectors. So what I'm saying is that at any point along some surface, I can create a normal vector. That's what the yellow vector is. And I've told the computer to plot a bunch of those. But the idea is at any point, there is a normal vector. All of these vectors that I have are pointing outwards if I'm sort of from the perspective of the origin. But I could also come up with a series of normal vectors that all pointed inwards as well. And indeed for this surface, if I restrict myself to unit normal vectors, so normal vectors of length 1, there's actually two consistent choices. I could have all of the vectors pointing outwards or all of the vectors pointing inwards. Either would be entirely fine. But what is key here is that all of the choices I have made are sort of consistent. I mean, I could have done something like where at one point it's pointing outwards, and then if I move over a tiny bit, it flips around and is pointing inwards. It could be that the vectors are going up and down, all beside each other. This would be a discontinuous assignment of unit normal vectors to my surface. So this motivates my definition. We have a smooth surface. We're going to call that being orientable if there is a continuous field of unit normal vectors assigned on that surface. I know this might seem like something you can always do, but actually it turns out that this is not always possible. Consider, for example, the Mobius strip. The Mobius strip is fascinating because it only has one side. Well, let me show you what I mean. Okay, so to make a Mobius band, I'm going to start with just a strip of paper. And my strip of paper has two different sides to it. In fact, I'm going to make this even clearer by taking a pen and marking one of those sides. And the result is that we have an orientable surface right now, two different sides. For example, I could imagine my pen illustrating a normal vector, and it could be assigned either to one side or to the other side continuously. And I could even go and take this and form it together to make a cylinder. And a cylinder is also an orientable surface. There's two sides, the side that's got the pen on it and the side that doesn't have the pen on it. And I can have normal vectors that go along the outside or normal vectors that go along the inside. But to make a Mobius strip, what I'm going to do is instead twist it once before I attach it. And this creates a Mobius strip. I'll just tape it together at that spot just to keep it nice and secure. This is sort of what it looks like. And now the question is, do I have one side or two sides? Well, it turns out there's only one side. For example, if I take my finger and I track along, okay, I'm gonna go all the way along the outside edge here where I've got that black, fell off, I've got the black pen. It comes along, it's now doing, well, I just haven't removed my finger. Comes all the way along and I'm exactly back where I started. But here's the thing, I never removed my finger, at least except for that one time by accident. So there's really only one side to this. The portion that used to have the black line and the portion that didn't have the black line, well, now they're on the same side. So now I'm going to explore whether I can continuously assign some normal vectors. So I'm going to put my normal vector right here where my thumb is. And I'm going to follow it around, normal vectors all the way along, normal vectors all the way along, and now what's happened? The normal vector is exactly the opposite of where it started. It began here, I went all the way around, and now it's down beneath. So there's no way to continuously assign vectors. If I'd assigned it over here and I come around in a continuous way right beside where I exactly started, the normal is now the negative of what it was at the beginning. I cannot continuously assign normal vectors to a Mobius strip. So the point is that the Mobius strip is not an orientable surface. There's no way I can continuously assign a unit normal vector field along that surface. Now for us in vector calculus, we look forward to the big theorems that are going to come up. We're going to restrict ourselves to the orientable case. We're going to be able to make claims about orientable surfaces where we're able to prescribe these vectors to them. Now, this whole concept is somewhat analogous to what we did back with curves. So previously, I might have talked about a curve R of t now with a single parameter t. In the plane would be g of t I hat and h of t j hat. And here my t would be between two values, say a and b. There is an implied orientation here, which is that t increases. So for example, if I have this going from some point A to point B at the times t equal to little a and t equal to little b, then it might travel from, say, left to right. But if I reverse this and went from t going from b to a getting smaller, then it might be the exact same thing, it's just I would visually think of it going the other direction. So when I had a curve, one of the things we would often do is just put a little arrow on it. And the arrow would tell us the direction along that curve we were intended to travel. It's sort of like an orientation for the curve. So the same issue is going to come up with surfaces. If I have an orientable surface, and we're going to be computing a bunch of things about those orientable surfaces coming up in future videos, I also then need to tell you which way is it oriented. I need to tell you a prescription of which of the two different choices of unit normals we're going to use. So this means that if you're given a surface, there's two issues. First of all, you have to decide whether the surface is orientable or not orientable. And as we've seen, it could be either. If it's orientable and we're going to do the types of calculations that we're going to do in future videos, that's great. But you can't just tell me the surface, just in the same way you couldn't just tell me the curve. You have to tell me its orientation as well. You have to tell me which of the two different choices of orientation are you prescribing. Now, when we've talked about surfaces previously, we've often described them parametrically, as in we have some position vector r of u and v. And then as long as our parameterization was nice enough, we could always get a normal vector, as we've seen before, by taking ru cross rv. Obviously, you have to be able to take these derivatives. And then once you got a normal, you could multiply this by any non-zero constant. And in particular, what you could get is two different unit normals, ru cross rv divided by its length, and then the negative of that. So you'd have one unit normal pointing one direction and the negative of that on the other side. Alternatively, if you had described your surfaces implicitly, f of x, y, and z equal to c, then we'd seen that a normal that you could get was the gradient of f, and then your choices were the unit normal's gradient of f divided by its length, and the negative of the gradient of f divided by its length.